Mockholtz, and you are listening to Looking Up with Don. This is the Looking Up with Don podcast, episode number 6 for the week of February 12th, 2020. Happy birthday, Mr. Lincoln. The related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ, 2 H's.com. What's up in the sky this week? As our week begins on Wednesday, February 12th, the moon is in the morning sky and reaches third quarter this weekend. That gives us a dark evening sky, and this week we're going to be taking advantage of that and looking at a lot of neat stuff. On the morning of Tuesday, February 18th, the moon passes in front of the planet Mars as seen from the northern part of North America. The moon will be 24% full, which is nearing the crescent phase, and Mars will disappear behind the lit portion of the moon and emerge from behind the dark limb. The next day, Wednesday, February 19th, the moon occults the planet Jupiter, but only from the very southern part of the world. But don't give up on this event. With a 16% illuminated moon near the planet Jupiter, that day, February 19th, would be a good opportunity to see the planet Jupiter in the daytime through a telescope. I am not making this up. Jupiter can be observed in daylight through the telescope and in Colfax, California, during some of the 4th of July gatherings that are held each year on the 3rd of July, but that's a different story. We have shown Jupiter to the public in daylight. And most people looking through the telescope in the daylight could see Jupiter. We've also shown the star Sirius in daylight too. From North and South America, at midday, the moon passes 1 to 2 degrees south of Jupiter, depending upon whether you're in North America or South America. Finding the crescent moon in the daytime sky may be the most difficult part of this exercise. But once you do that, focus on the moon, then sweep north with low power and a wide field eyepiece back and forth until you find Jupiter. Even at low power, it will appear as a tiny disk. Jupiter in the daylight time is amazing. The bands in the atmosphere are visible, but I have never been able to see the moons of Jupiter in daylight, which are around magnitude 5 to 6. So see what you can see next Wednesday, February 19th. In the evening this week, you'll see the planet Venus in the southwest. It's on the inside orbit going around the sun, so it's catching up to us. Early this week, you might still be able to catch the planet Mercury much below Venus and setting about 75 minutes after the sun, much less so by the end of the week. I was able to observe Mercury a few nights ago. It's very bright, but it is down by the horizon after sunset. As with last week, after you locate Mercury, look up at Venus, then down at the Earth, and you've seen our first 3 planets. Without the moon in the sky, take a few minutes to look things over. What is known as the Winter Milky Way runs overhead from northwest near Cassiopeia and through the constellations of Riga, Orion, and down past the brightest star in the sky, Sirius. The Milky Way is our galaxy, which is like 2 plates put together face to face, and we're 2/3 of the way from the center to the edge. When we look up in this area, we are inside looking out through the rim. We're looking away from the center of our galaxy. In the summer months, we'll be able to look toward the center of the galaxy when we examine the summer Milky Way. And don't forget to check out the star Betelgeuse in Orion. Using Star Map 1 from Podcast 6, make a magnitude estimate of it this week. Is it getting brighter, dimmer, or holding steady? You be the judge on that one. In the morning sky this week, you'll find the planet Jupiter low in the southeast. If you stay out long enough, you'll find the planet Saturn rising about 90 minutes before the Sun. So ponder this for a few minutes. Here in the morning sky we have from top to bottom Mars, Jupiter, and Saturn. Remember in the evening sky we saw the planets Mercury, Venus, and Earth. What more could you ask for? The next planet out is the planet Uranus. Do you want to see that one too? Well, we'll be covering that later in the podcast. Comet Pan-STARRS, Comet 2017 T2, is still in our evening sky, and we looked at it a couple of weeks before the moon entered the sky. Now that the moon's out of the sky, let's take another look at it. It's still approaching its closest point to the Sun. That'll be in a couple months, and it is shining at about 9th magnitude. It's presently 160 million miles from us and 180 million miles from the Sun. Its path is marked on Star Map 2 from Podcast 6. You will need a telescope to see Comet Pan-STARRS, but give it a look this week. The International Space Station is not going to be visible to those in mid-northern hemisphere this next week, but for those in the southern hemisphere, it will be visible sometimes in the evening and sometimes in the morning. Those near the equator will also be able to observe the International Space Station in the morning sky some nights and in the evening sky on other nights. Go to the website heavens-above.com, enter your location, and find out where and when to see it. The Unaided Eye Challenge. It's constellation time again. Let's add the constellation Cassiopeia to our knowledge. It's visible in our evening sky, high in the northwest as the sky darkens. It looks like the letter W, or the letter M, or maybe a 3. Possibly the sigma symbol, uppercase. This constellation is far north, and from much of the northern hemisphere, it circles the North Pole each night. What symbol it looks like depends upon where it is in the sky. The constellation Cassiopeia is identified on both Star Map 1 and Star Map 2 for this podcast number 6. These nights, as you go out and face north, it looks like the letter M. It has 5 main bright stars, and Cassiopeia, with the Milky Way running through it, is full of open star clusters and nebula. If you have binoculars, take a few sweeps through this group. This is a good constellation to know. From much of the northern hemisphere, it's visible all night, every night, and it is on the opposite side of the North Star from the Big Dipper. When the Big Dipper is low, Cassiopeia is high. When the Big Dipper is high in the sky, Cassiopeia is low in the north, skimming the horizon. Cassiopeia is a good friend to get to know. It's like a friend you'll never lose. For the binocular challenge this week, we'll be looking at a very large open star cluster, which is only 150 light years away. It is the Hyades, spelled Hyades. The best way to find it is to look for the bright star Aldebaran high in our evening sky. The Hyades star cluster is labeled on both Star Map 1 and Star Map 2 of Podcast 6. Take a gander around Hyades with binoculars. It's about 5 degrees across, and is defined by the V-shaped pattern of bright stars with the star Aldebaran on one end of the V. Now, Aldebaran is not part of the open cluster. It's a foreground star only about 65 light years away. What color are the stars? Is there an apparent center to the cluster? Take a look and determine that for yourself. Our telescopic challenge this week is the distant planet Uranus. This planet was discovered on March 13th, 1781 by William Herschel from Bath, England. You can go to the Herschel house today and stand in his backyard garden from where he discovered this planet. Uranus is now in our evening sky, north of the circlet of Pisces, and is marked on Star Map 2, Podcast 6. It's at magnitude 5.8, and it's 20 times farther from the Sun than we are. In the telescope, it should appear blue-green in color, although I usually see it more as green than blue. You can crank up the magnification a bit. At a size of 3 arcseconds, you should be able to see it as a disk. Those with large telescopes might be able to pick up a couple of the moons at about 14th magnitude. This week's fun fact: my comet hunting theory, devised for visual comet hunting. I devised this theory back in 1978, and it helped to explain why I wasn't discovering any comets and how to improve my comet hunting techniques. I've always been, and I still am, a student of visual comet hunting, and I still apply the theory today. Before we go to the theory, a little background. I began comet hunting the week I graduated from high school, June 1970. Over the next few years, I did a few hours here and a few hours there. And in the second half of 1974, knowing that I'd be getting out of the Army in November 74, I searched for an astronomy project to keep me looking up. I chose comet hunting and decided in late November 1974 to start systematic searches on January 1st, 1975. I had read in 2 different comet books that it would take 100 to 200 hours and also maybe 300 hours on the average to find a comet. An interview in Eclipse magazine with William Bradfield seemed to confirm this. In 1975, I did 307 hours, no comet discovery. 1976, an additional 553 hours, no comet discovery. 1977, 504 hours, still no comet discovery. So in 3 years, 1,364 hours and no comet discovery. I had to wonder what was going on here. If no one else was visually discovering comets, then the answer was simple. There's no comets to find. We're all searching a sky devoid of comets. But that wasn't the case. Beginning in the beginning of 1975 to the end of 1977, 3 years, 10 comets were found visually by other amateur astronomers. I figured I was doing something wrong. Dr. Marsden of the Smithsonian Astrophysical Observatory would send me pre-discovery positions of the comets found visually, usually within a week after they were discovered. I did not have the computing power, what was computing power in the late 1970s, to do this myself, so I relied on him to give me these positions. Then I would see if I had swept the pre-discovery areas prior for each comet being found by other comet hunters. I soon realized that if I was to become a better and more efficient comet hunter, I had to work in 3 areas. For each comet that I missed, it was usually only 1 or 2 of these 3 conditions or factors in which I had failed. So my visual comet hunting theory states that 3 conditions must be met in order to discover a new comet. If you meet all 3, you will find a comet. If you fail to find a comet that others have found, it's usually because you failed in 1 or more of the 3 areas. Let's go through each of the 3 conditions that must be met to discover a comet. And also remember that this is intended for someone who's intentionally searching for a comet. When I give a comet hunting lecture to astronomy groups, I discuss this, and the audience always laughs at the first one. It seems so obvious, but it's vital. The first one is, are you ready for this? Position. You must be looking at the comet. Done laughing? Not yet? Okay, so let me explain. The celestial sphere is 41,253 square degrees. Let's exclude the south part of my southern horizon for a minute, and we're now at about 30,000 square degrees. If you want to also exclude the twilight and sunlight areas, we now have about 25,000 square degrees. So I ask you, if you were going to go out and comet hunt tonight and cover an area of 1,200 square degrees, which is about a 40 by 30 degree area. And back in those days, that would take me 2 to 3 hours. Which part of the sky would you sweep? And be specific. You see, it's not so easy, is it? In one session, you can cover less than 5% of the sky. So would you cover the morning sky or the evening sky? The polar region, the equatorial region, the southern sky? And then the next night, would you cover an adjacent area or a completely different part of the sky? You don't know where the comets are when you go out comet hunting. And comets slowly move across the sky, so that an area you cover tonight might have no comet in it. In a few nights, a bright, undiscovered comet might be moving through it. Here's an example. I discovered my second comet on May 27th, 1985, from Camp Oaks in Big Bear, California, at the Riverside Telescope Makers Conference. The comet was 9th magnitude and 49 degrees from the sun in the morning sky at Discovery, which was the last day of the conference. Do you know what is at the Riverside Telescope Makers Conference? Telescopes. Hundreds of them. And people who know how to use them. Some of the top amateur astronomers are at that conference with their best telescopes. And of all those telescopes there, did no one else discover the comet? Why did no one else find it? The answer, position. No one looked in the part of the sky where the comet was located. If they had, they would have discovered the comet. It was bright enough for nearly every telescope to pick up. Another example, Comet Hale-Bopp. A couple of nights before Hale and Bopp found it, I swept an area about 10 degrees north of the comet's position. I missed it because I wasn't looking in the right location. Another example, the discovery in July 1975 of Comet Kobayashi-Berger-Milan. Most comet hunters do not cover areas 133 degrees from the sun where this one was found. Kobayashi did, and he was looking for a comet. While Douglas Berger and Dennis Milan were not looking for a comet, they were observing the globular cluster called M2, and the comet was nearby. Most of us comet hunters missed this comet because we were all looking in an area closer to the sun. We were not looking in the right position. As an aside, I've seen that most comets discovered by those not looking for a comet have two things in common. They're usually found far from the sun in degrees, that's called elongation, and they're often found near known bright celestial objects, which is what they're looking at when they find the comet. And remember where earlier I said exclude the areas south of my southern horizon, which is about 10,000 square degrees? Let's now discuss those because they cannot be excluded, really. Some comets are discovered too far south for me to see, and William Bradfield of Australia found many of them. But sweeping the areas south of my southern horizon is not something that I can do unless I move to a location closer to the equator. But in all other situations, the lesson is clear. Cover as much sky as you can because you don't know where the next comet is hiding out. Some areas are more likely to hold undiscovered comets than others, but the lesson that I learned early on is anyone can discover a comet in any part of the sky at any time. So the first factor is position. The second is brightness. The comet must be bright enough for you to see it. You can sweep an area down to, for example, magnitude 10.5, and if there is an undiscovered comet in the area, and you do have the right area this time, you're looking right in where the comet is, but that comet is magnitude 12, fainter than what you can see, you will not discover it. It will be too faint for you to see. Limiting magnitude is determined by many things: your eyes, sky contrast, telescope aperture in contrast, the rate of sweep, the field of view, among other things. Someone might say, I can see galaxies in my 10-inch telescope as faint as 12th magnitude. But someone sweeping the sky, not told that something is in such and such a part of the field of view, and sweeping at a rate such that the object flows across the field of view in 2 seconds, may miss something even as bright as magnitude 11. It's one thing to hunt down galaxies from a map showing their exact location, and quite another thing to acquire the same object flowing across your field of view. Additionally, comet hunters generally are not looking high in the sky where the atmosphere is thinner and there's less light pollution. We look toward the horizon. And I'm almost always less than 20 degrees high, and most mornings average 10 to 15 degrees high. That low altitude makes it harder to see extended objects. An example: periodic comet Takamatsu was discovered in the morning sky at magnitude 9.4 on July 30th, 1984. My records show that I swept over it on 9 occasions in the previous 4 months. It was there, I was there, but I failed to see it because it was too faint. We strongly suspect it outburst shortly before Takamatsu discovered it. This is a periodic comet, and on subsequent visits, it hasn't performed very well, so we do know that it varies some in brightness. Okay, so wanting to comet hunt in all areas of the sky and going deep, that is, seeing faint stuff, we do have to make some trade-offs. To cover a lot of sky, I could just simply sweep at a faster rate. No, wait. If I sweep faster, I'll not be able to pick up comets as faint as if I sweep slowly. On the other hand, to see faint objects, maybe I'll just get a larger telescope. No, wait a minute. Bigger telescopes means smaller field of view, and now it will take me longer to cover the sky, and as a result, I'll see less sky. So I can cover a lot of sky or see faint stuff, but not both. One partial solution is to find a darker sky, where you can see fainter while still sweeping at the same rate. Many comet hunters either move to a darker location, I did that twice, or commute each session to a dark site. Another partial solution is to spend more time comet hunting. Then you could use a larger telescope or use what you've been using and just sweep slower. Just spend more time out there. However, the prime areas for comet discovery are near the sun, in the near twilight areas, and those parts of the sky are above our horizon and available for searching only a couple hours each night. In next week's podcast, I'll discuss why I found some strange bright comets, while other comet hunters were finding the fainter comets, but that will be next week. Okay, so now we get to part 3 of the comet hunting theory. That is, you must find it before others. Up to 3 names can be on a comet, and after the first person finds it, typically, and this was not a hard and fast rule, the door would remain open for another 24 hours to see if anyone else would find it. More recently, though, a suspected comet can be placed on the NEO suspect page with the date of observation, position, and magnitude for everyone to see. When that happens, it becomes difficult for others to later prove they independently found it. But once a comet is discovered and named, you cannot discover that comet. And the number of discoverable comets is limited at a rate of about 3.3 new comet discoveries per year for visual comet hunters from 1975 through 1994. So in a sense, we compete with each other to find a limited number of comets. The moon phase controls to a great extent where and when we sweep. One could say that if there was no moon, a comet hunter would never sleep. Ha ha. A week or more after full moon, as the moon gets fainter each morning, we go out and look for comets in the morning sky. In the late 1970s, I noted that many of the Japanese comet hunters were finding comets in the morning sky on the day of new moon. Here's an example. On August 6, 1988, I discovered my fourth comet in the morning sky at magnitude 8.6. The moon was 33% full. That is a big crescent, higher in the sky than the comet. The comet was confirmed the next morning. A day after that, 5 Japanese comet hunters picked up the comet, but they were too late to get credit. Here's an area where I failed on 2 conditions. Uranus discovered his second comet on July 18, 1983, at magnitude 10.7. It was near M77 in the morning sky. I swept that area the day after he found it, not knowing he had found it, and I did not pick it up. I was using my large homemade binoculars. So I failed on 2 accounts. It was too faint for me to see, and I was a day late. But I was in the right position. A change I made due to that incident was to lower the binocular mount so that I could sweep the sky while sitting rather than standing. That stabilized me, and it slowed down the sweep rate in order to pick up fainter objects. I continue to use my comet hunting theory for my present work. My aim is to strive to cover as much area as I can, to see as faint as I can, and get out there frequently and promptly to search for comets. Now for fun with the marathon. The Messier Marathon's a yearly activity to observe all or nearly all of the 110 galaxies, clusters, and nebula in the Messier catalog in one night. The best time to do this is in late March of each year. This year, many will be doing this on March 28th, although I have seen at least one astronomy club that's going to do it on March 21st. To successfully run the marathon, it helps to have an observing order. It helps you to work your way across the sky from the western sky, where objects are setting, all the way over through the eastern sky. Now, I assembled one in 1978, refined it over the years, and it's been very helpful in systematically finding as many of the Messier objects as the sky allows you to see. You can download it from my website. It's in the last podcast, Podcast 5, Search Sequence. And while you're at it, you also might want to download Podcast 6, Map 3, 2, which shows the Messier objects that we'll be discussing this week. When we left off last week, we had picked up the first 15 objects in the Messier Marathon. Now we move high in the sky for the next 5 objects. We go 20 degrees north from Orion to Taurus, and we pick up M1. Now, most years, this is an easy object, but be careful. In late March, if you're out marathoning with the moon about 35% full, and that won't happen this year, but occurs in some years, the moon will be in this area, and M1 may disappear in the moonlight. After M1, you make a 10-degree move to the open star cluster M35. You might notice a small dense cluster on the southwest corner of M35. This is 2158. From here, you go north and west to M37, then 4 degrees further over for M36, and finally continue on to M38. Now, having finished up these Messier objects high in the sky, we move further south again to pick up a circle of 5 open star clusters. Our next one is M41, an open star cluster about 4 degrees south of the bright star Sirius. By the way, sometimes when I'm set up and waiting for the sky to completely darken, I go over to Sirius, drop down 4 degrees, and M41 ends up being the first object of the night. Anyway, After you've seen M41, go 15 degrees to the left to pick up M93, and it's about the same brightness as M41, but smaller, and it's rectangular in shape. Next, we move upward about 10 degrees to M47, which is brighter and more easily visible than the next one we'll see, M46. And because 47 is brighter and more easily visible, we see that one first, then we hop over to M46. Be careful when you go from M47 to M46. There's a few open star clusters in the area that could be mistaken for M46. M46 is about 1.5 degrees east of M47, and on the northeastern edge of M46, you might also pick up the small planetary nebula known as NGC 2438. There are two more objects, both open clusters in this area. For M50, go 12 degrees to the northwest, and this open cluster stands out even in the Milky Way background. That's M50. Then, one of the most difficult objects for me to find is M48. There's just no bright stars nearby, so it might take some time for you to find it. One way to get to the area is to use the two bright stars in Canis Minor. Draw a line from the second brightest star through the brightest, Procyon, and keep going 3 times that distance to M48. Our last two objects for this week are in the constellation Cancer. M44, the Beehive cluster, is visible to the unaided eye. Now, as with M45, you do need to see this through your main scope and not just your finder scope. Finally, we go to M67, a small open star cluster about 8 degrees south-southeast of M44. So there you have it, the first 28 objects of the Messier Marathon. You've covered the first 25% of the Messier catalog. Next week, we're going to head east to Leo and then north to cover the next 20 objects. For those in the Phoenix area, on Friday, February 21st, I'll be delivering a lecture about the Messier Marathon to the East Valley Astronomy Club. Go to their website, evaconline.org, for details. Once again, that's EVAC for East Valley Astronomy Club. Then the word online.org for details. Once again, the related website for this podcast is donmacholz.com. That is spelled DONMACHHOLZ.com, 2 H's. God willing and pod willing, I'll be back next week for another episode of Looking Up with Don. We will discuss what's going on in the night sky, more about the Messier Marathon and the next 20 objects, and I'll be discussing different visual comet hunting types. Thank you for listening. See the sky this week? I'll see you next week.